Welcome back to the deep dive. Today, we are really getting into the weeds, not just looking at individual security controls. We're unpacking what feels like the ultimate architectural blueprint for massive scale cloud operations.
hmm
If you work in the enterprise, if you're handling compliance, maybe you just want to understand, the gold standard for deploying stuff in the cloud securely, you really need this.
Yeah, this is foundational stuff for large environments.
We are diving deep into the AWS Security Reference Architecture. You'll hear it called the AWS SRA.
That's precisely right. And look, the AWS SRA it's much more than just a checklist of services you should turn on.
Right.
It's really this comprehensive, holistic set of guidelines. It details how you structure your entire organization in the cloud. We're talking accounts, network plumbing, your security services,
All of it.
all aimed at achieving a robust and, importantly, compliant security posture, especially, as you said, in those large multi-account setups. That's where it really shines.
So our mission today really is to cut through maybe the complexity and give you the synthesized core knowledge. We spent a lot of time poring over the official AWS prescriptive guidance documentation,
Yep, the source material.
including those critical updates from August 2025 that are noted.
Yeah.
We want to map out the SRA's recommended structure, the kind of mandated service centralizations, the operational processes, even down to the nitty-gritty like forensic readiness protocols.
And it's really vital context, I think, that this guidance is described as a living set of guidance.
Okay, so it changes.
Constantly. It
Yeah.
has to, right? It's revised all the time to reflect, the evolution of AWS services themselves and also, frankly, the escalating sophistication of threat actors. They get smarter. The guidance has to adapt.
Makes sense.
And this whole architecture, it's predicated on a really solid foundation. There are underlying frameworks and I'd say almost unbreakable principles that govern it, which is honestly where we absolutely have to start this deep dive.
Right. Lay the groundwork first. Okay, let's unpack this foundation then. The SRA, as you said, doesn't stand alone. It's fundamentally aligned with, built upon some of AWS's core doctrines.
Exactly. Specifically, you're looking at the AWS Cloud Adoption Framework, or CK, and the AWS Well-Architected Framework. These are the bedrock.
Okay, let's touch on those briefly. The CK, that's more about the organizational shift, right?
Yeah, the CK provides that high-level structure for how an organization should actually approach cloud adoption. It looks at things like business drivers, people, governance, platform strategy. It's quite broad.
But for the builders, the people actually deploying things.
For the builders, the SRA leans really heavily on the AWS Well-Architected Framework. I mean, this framework is pretty much the definitive roadmap for deploying resources securely, efficiently, reliably, all the oddities.
And within that framework, they hammer home those 6 pillars, don't they? The things that define kind of operational excellence in the cloud.
Correct. Yeah, the 6 pillars. You've got operational excellence itself, reliability, performance efficiency, cost optimization, sustainability, which is increasingly important, and of course the one most central to our discussion today, security.
Right.
And the idea is, if you design your architecture with all 6 of these pillars in mind, so you're not just thinking about security in a silo, but how that security operates, how it might affect reliability, how you sustain that posture cost effectively, you fundamentally increase your chances of, long-term business success. The SRA, you could say, is essentially the detailed blueprint for executing that security pillar, but at serious scale.
Okay, that makes sense. It situates security in the bigger picture.
Yeah.
Now, before any customer, configures even a single resource, there's this core concept they absolutely must internalize. It defines cloud risk, the shared responsibility model, the SRM.
Yes, the SRM. We hear this term constantly, don't we?
All the time. But what is the exact delineation according to the SRA? Where's that line drawn?
Okay, so the SRM it's the critical mechanism. It separates ownership, who's responsible for what.
Yeah.
And it dictates pretty much every design decision within the SRA. It's often summarized simply, AWS handles this, you handle that.
Yeah.
But the details matter, like tremendously. The model fundamentally mandates that AWS is responsible for security of the cloud.
Security of the cloud. Okay.
Think of this as the physical stuff. The security of the data centers, guards, gates, concrete the underlying infrastructure, the host operating system that runs the services, the virtualization layer. AWS maintains the structural integrity and the operation of the services themselves.
Got it. So the building, the power, the core compute fabric.
Exactly.
Yeah.
And the other half then is security in the cloud. And that belongs entirely to the customer. That's you, the person consuming the services.
Right. So that's where our responsibility kicks in. Precisely. And this covers, well, everything you put on that infrastructure. Configuring the guest operating system on an EC2 instance, for example, the application software you deploy. Those critical network settings like route tables, security groups, you configure those.
Mm-hmm.
Managing identity and access management,
Mm-hmm.
IAM, who can do what. And crucially, things like server-side data encryption. If you configure it, if you manage the code running on it, if you put data in it, securing that specific part is your responsibility.
Okay, to make this really actionable for you listening, let's contrast the level of responsibility. Maybe pick two common services, like EC2 versus S3.
Oh, a fantastic idea. Yeah, that makes it concrete. Okay, consider Amazon EC2. You launch an instance, right? A virtual server.
Yep.
AWS maintains the underlying hardware, the physical host, the hypervisor. But you are responsible for patching and securing the guest operating system, Windows, Linux, whatever you install.
Right. OS updates, security patches. Exactly. Configuring the firewall rules on the instance itself, like IPTAbles or Windows Firewall. Monitoring the user space, the applications running on it. It's, pretty hands-on security management, much like an on-prem server in many ways.
Okay. Now, shift focus. What about a managed service? S3 maybe, or
Yeah.
DynamoDB?
Right. Totally different picture. With something like Amazon S3 or DynamoDB, AWS absorbs a huge chunk of that burden. They manage the infrastructure, the patching, maintaining the platform itself. You don't even see an OS. Your operational burden shrinks dramatically. Your focus shifts entirely to the data itself, determining its classification as this public data, sensitive PII, financial, choosing the appropriate encryption mechanisms, should it be KMS, SSE, S3, and enforcing the strictest possible IAM permissions for who or what can actually access that data.
So less about the infrastructure, more about the data governance and access control.
Exactly. And the SRA is designed specifically to help you manage that customer side of the responsibility spectrum consistently across potentially hundreds or thousands of accounts.
That context is absolutely crucial because, yeah, the operational overhead, the skills you need, it changes entirely based on the service model you choose. Okay, with that shared responsibility model firmly in mind, let's look at I think there are 7 foundational security design principles.
Yes. 7 core principles.
The ones that must govern every single structural decision you make when you're implementing this SRA blueprint.
These are like the philosophical non-negotiables. You build everything on these. Starting with number 1, implement a strong identity foundation.
Identity first, always.
Always. This means absolutely eliminating reliance on long-term static credentials, like access keys where possible. Centralizing identity management, think IAM Identity Center, and rigorously enforcing the principles of least privilege and separation of duties.
So only the minimum permissions needed for the shortest time necessary.
That's the mantra. Your identity's users, roles, applications should only have the bare minimum permissions required to do their specific job, and ideally, only when they need them. No standing privileges if you can avoid it.
Okay, number 2, enable traceability. Visibility, right?
Visibility is key. This is where your ability to see what's happening comes from. If you can't observe an action, if you can't log it, you simply can't secure the environment effectively.
Makes sense.
So this means comprehensive monitoring, detailed logging, and auditing of pretty much everything, every API call, every configuration change, every user action, and importantly, doing it in near real time.
And not just logging, but acting on it.
Absolutely. We're talking about generating meaningful alerts from those logs and, ideally, integrating those logs with systems that can automatically investigate or respond to anomalies. Think CloudTrail, config, GuardDuty logs, all feeding into a central system.
Got it. Okay, principle 3. This sounds like classic security strategy. Apply security at all layers.
Yeah, this is pure defense in depth applied to the cloud stack. You absolutely must implement controls, both preventive controls, the ones that stop bad things happening.
Like firewalls, SCPs.
Exactly. And detective controls, the ones that tell you when bad things are happening.
Well, like GuardDuty, Security Hub findings.
Right. And you need these controls across the entire stack. From the network edge, think CloudFront, WAF, down through the VPC, the load balancing layer, the compute instance itself, the OS running on it, and even within the application code. Don't ever rely on a single defensive boundary. Assume any layer can be breached.
Okay, multiple hurdles for an attacker. Principle 4 tackles the challenge of doing this consistently, everywhere. Automate security best practices.
This is crucial for scale. Manual security processes are just too slow, they're expensive, they're prone to human error, and they become brittle very quickly in dynamic cloud environments. The SRA really demands that you treat security controls as code. Think infrastructure as code, or IAC. Managing your security policies, your configurations, your deployments through version-controlled templates, CloudFormation, Terraform, CDK, whatever your
So
flavors.
consistency and speed.
Consistency, speed, repeatability, and auditability. And ensure you can apply the same baseline everywhere and respond rapidly if you need to make a change across the board.
Right. Okay, number 5 brings us to the crown jewels. Protect data in transit and at rest.
Yeah, ultimately, security is often about protecting the data. This principle begins with data classification. You have to understand what data you have and how sensitive it actually is. You can't protect what you don't know you have.
True.
Once classified, then you apply the appropriate protective measures. That usually means encryption TLS for data in transit, KMS, or other server-side encryption for data at rest. It could also involve tokenization for certain types of data, and of course, wrapping it all in stringent access controls to ensure only authorized entities can actually get to it.
Okay. Number 6 is maybe the most counterintuitive one for people coming from traditional IT backgrounds.
Yeah.
Keep people away from data.
It does sound a bit strange at first, doesn't it?
Yeah.
But this principle directly addresses a huge risk factor:
Mm.
human error or sometimes intentional misuse.
The insider threat or just mistakes?
Exactly. The goal here is to design your workflows and use automation tools that reduce, or ideally completely eliminate, the need for manual processing or direct console access to sensitive data stores. Think automated reporting instead of analysts querying production databases directly.
Less hands-on access minimizes the risk surface.
Precisely. Minimize the opportunities for humans to mishandle sensitive data, accidentally or otherwise.
Got it. And finally, number 7, acknowledging reality. Prepare for security events.
Yeah. Assume breach. We have to operate under the assumption that a security incident is a matter of when, not if. It's inevitable at some scale.
So you need a plan.
Therefore, the SRA requires preparation. This means defining clear roles and responsibilities for incident response, training your personnel on those roles and the tools they'll use, and creating very clear incident management policies and, again, automated processes designed specifically for cloud environments, which can react much faster. We'll dive into this more later.
Okay, that foundation of principles really sets the tone for the whole architecture. Now we get into maybe the core structure that defines large-scale AWS security. The multi-account strategy centrally managed through AWS organizations. When we talk about potentially hundreds, even thousands of accounts, why? Why is that isolation necessary? Why not just, one massive account if we think we can manage IAM permissions really well?
Right, it's a common question. The simple answer is the account boundary. An AWS account provides the ultimate security, access, and critically billing boundary. It is the strongest blast radius delimiter you have in AWS.
Blast radius. Okay, limiting the damage.
Exactly. Using multiple accounts guarantees resource independence and, ideally, absolute isolation between different workloads or environments. If one account, say a development account, is compromised, the breach is contained within that account's boundary. It prevents easy lateral movement across the entire organization's cloud footprint. That isolation is paramount.
And the SRA is specific about how these accounts are grouped, right? Using organizational units, OUS.
Yes, and this is key. The SRA specifies that these accounts must be organized into organizational units, OUS, based primarily on function or specific compliance requirements. For example, you'd have an OU for infrastructure, an OU for security tooling, maybe separate OUs for PCI DSS workloads or high-pay compliant workloads.
So not just mapping it to your internal corporate reporting structure, like the finance department gets an OU, marketing gets an OU.
Generally, no. While that might seem intuitive, it often doesn't align with security and operational needs. You group by function, like all production application accounts under a workload's OU, or by compliance boundary to apply specific controls like SCPs effectively.
Okay, function and compliance over org chart. Now, within that account boundary, the very first identity created, the root user, is, well, it's potentially a massive security liability if it's not managed correctly.
Oh, absolutely. It's often called the nuclear key for the account. It has maximum unfettered permissions, and crucially, it cannot be constrained by standard IAM policies.
Wow. Okay, so what's the rule?
The SRA rule here is unequivocal, crystal clear. The root user must not be used for day-to-day tasks, period. It should only be used for the very small handful of specific account management or recovery tasks that explicitly require it.
And in an AWS organization setup?
In an organization managed by AWS organizations, the absolute best practice, strongly recommended by the SRA, is to centrally disable root sign-in capability for all member accounts using an SCP. Then you delete the root user's password, delete any access keys associated with it, and deactivate MFA.
Deactivate MFA. That sounds wrong.
It sounds counterintuitive, but the idea is you lock it down so completely that it cannot be used normally. You keep the ability to potentially reactivate MFA through a support process only as an absolute last resort, a strictly controlled break glass recovery scenario if everything else fails.
Ah, okay. So it's there, but essentially unusable unless disaster strikes.
Exactly. And for new accounts provision, perhaps via a tool like AWS Control Tower following SRE principles, they should never have operational root credentials active from day one. Lock it down immediately.
Right. Okay. Let's map out the high-level architecture now. Let's identify the specific OUs and those critical, dedicated accounts within them that really form the backbone of the SRA. Where do we start?
We start at the very top with a foundational account, the org management account. This is sometimes called the payer account or the management account.
This is where the organization itself is created.
Yes, this account sits at the absolute top of the hierarchy. Its duties are purely administrative. Things like handling consolidated billing for all member accounts, orchestrating account provisioning, maybe using AWS Control Tower's Account Factory if you're using that service, and critically, managing those organization-wide preventive guardrails, particularly service control policies, SCPs. Very little else should run in this account. Keep it clean.
Okay. Org management account at the top, minimal function, maximum control. Next, OU.
Next, we typically move into the security OU. This is a critical one. It houses the two most important specialized accounts specifically for governance and monitoring.
Right, the brains in the vault. Let's start with the first one, the security tooling account.
Okay, think of the security tooling account as the organizational security nerve center. It's the central administrator account for almost all your detective security services.
So things run from here, looking into other accounts.
Precisely. It is configured using delegated administration, which we'll touch on, as the central administrator for services like Amazon Guard Duty, AWS Security Hub, Amazon Macie, AWS Config, IAM Access Analyzer, Firewall Manager, the list goes on.
So the security operations team, the SOC, they primarily work out of this account.
That's generally the idea. They reside here, they maintain that centralized visibility across all accounts, they manage the alerts, and they initiate remediation workflows, often triggered automatically from findings aggregated here.
Okay, security tooling, the command center. And the second specialized account in the security OU is the log archive account. Its purpose sounds pretty rigid. Immutability.
Its purpose is simple but absolutely non-negotiable. It exists for one reason: immutable, centralized storage for every single log generated across the entire organization.
Every log. From everywhere.
Every CloudTrail log, every VPC flow log, AWS config history logs, security service findings logs, Guard Duty Security Hub, etc., from all regions and all accounts. They all get shipped here.
And why the separate account? Why not just put the logs in the security tooling account's S3 buckets?
Integrity and access control. The reason for its strict isolation is to protect the availability and, crucially, the integrity of this critical evidence trail. To prevent tampering, access to the S3 buckets within this log archive account must be highly restricted.
Like super restricted?
Super restricted. Generally, only the ingest mechanism, maybe Kinesis Firehose, or increasingly the Amazon Security Lake Service, or specific tightly controlled managed IAMR roles, should have permission to write data to these buckets. Read access should also be extremely limited, perhaps only allowing Security Lake or Athena queries initiated from the security tooling account via assumed roles.
So the security operations team shouldn't be logging directly into the log archive account to look at logs?
Ideally, no. They should query or analyze the logs from the security tooling account using tools that access the log archive data indirectly. You want to keep direct access to that raw, immutable archive as minimal as humanly possible.
That makes a lot of sense because, yeah, if an attacker breaches a workload account or even the security tooling account, their primary goal might be to erase the evidence. Separating the logs makes that much harder.
Exactly. It adds a significant barrier. It makes evidence tampering exponentially more difficult. Okay, moving on from the security OU, we enter the infrastructure OU. This typically contains the network account.
The network account. This sounds like it acts as the sort of isolated gateway for the entire enterprise network in the cloud.
That's a good way to think about it. Yes.
Yeah.
It's designed to contain the broad cross-cutting networking services that connect everything together and to the outside world. Things like your central inbound, outbound, and potentially inspection VPCs. Your AWS Transit Gateway sits here. Your main CloudFront distributions, your central AWS WAF rule sets, and your AWS Shield Advanced Protection resources would typically be managed from this account as well. Maybe things like Route 53 resolver endpoints too.
And the benefit of pulling all that out?
By decoupling these critical network components from the individual application workloads, you achieve a really strong separation of duties. Your network team manages connectivity, routing, and perimeter defense from this central account, independent of the application teams deploying code in their own accounts. It simplifies management and enforces consistency.
Okay. Also, in the infrastructure OU, we often find the shared services account. What goes in there?
This is basically a utility account. It's designed to host common services that are utilized by multiple application teams or workloads across different accounts.
To avoid duplication.
Exactly. Reduce duplication, reduce operational burden. Typical examples might include hosting AWS IAM Identity Center configuration, if not in the org management account itself, perhaps running AWS Managed Microsoft AD for Enterprise Directory Services integration, or managing central AWS Systems Manager configurations and documents, things that many different application accounts might need to consume.
Okay, common utilities. And then finally, we reach the OUS where the actual business happens, the workloads OU, which contains the individual application accounts.
Yes, the workloads OU is usually a parent OU, and underneath it you'll have multiple application accounts. This is where the actual enterprise application lives. This is home for the EC2 instances running your code, the Aurora databases storing your business data, the application-specific S3 buckets, Lambda functions, and so on.
And these application accounts are then protected by all the guardrails and centralized services managed from the accounts higher up the chain: security tooling, network, org management.
Precisely. Which brings us back nicely to probably the most powerful centralized preventive guardrail. Service control policies,
Yeah.
SCPs. Remember, these are managed from the org management account, but applied down the hierarchy.
Right. SCPs centrally manage which AWS Service APIs can, and crucially, cannot be executed by any IAM entity users, roles across your entire organization, or within specific OUs or accounts.
That's the power. They act as a maximum permissions boundary.
Now, you mentioned earlier that SCPs can function in two ways: as a deny list or as an allow list. Can you explain the practical difference for someone setting this up?
Sure. The denialist approach is the standard default way most organizations start. By default, when you create an AWS organization, the root OU has an SCP attached called full AWS access. Basically allows everything. You then create additional custom SCPs that explicitly deny specific harmful or unwanted actions. For instance, you might create an SCP denying the ability for member accounts to leave the organization, or denying access to launch instances in unapproved regions, or preventing the deletion of critical logging buckets, or blocking root user access like we discussed.
So you start wide open and then selectively block the bad stuff.
Exactly. It provides flexibility while blocking known high-risk actions. It's generally easier to manage initially.
But the allow list approach sounds much more intense, far more stringent and restrictive.
It is. It's the security lockdown model.
Mm-hmm.
You typically see this mandated in highly regulated environments like finance or healthcare, where you need absolute certainty about what can and cannot happen.
How does it work?
Instead of starting with full AW access, you detach that policy. Then you craft SCPs that explicitly permit only the specific AWS services and specific API actions required for the function of that OU or account. Everything else is implicitly denied.
Wow. So you have to list every single API call you want to allow.
Pretty much. And here's the critical rule you have to understand. For any permission, API action, to actually be enabled for an IAM entity in a member account, every single SCP in the hierarchy, from the root OU down through any nested OU to the account itself, must explicitly allow that action.
So if even one SCP in that chain doesn't list the action, it's blocked.
It's blocked. Even if the IAM user has an identity policy granting administrator access, if the SCP allow list governing their account doesn't include, say, EC2 run instances, they simply cannot launch an EC2 instance. Full stop.
That sounds like a potentially massive operational burden to maintain those allow lists accurately.
It absolutely is. It requires meticulous configuration, deep understanding of the permissions needed by services, and careful testing. But the payoff is absolute assurance that nothing unauthorized, nothing unexpected can possibly run in those accounts. Maximum control, maximum effort.
Okay, a trade-off between flexibility and absolute control. Now, all these distributed security services, guard duty finding something in account A, Macy scanning S3 in account B, config rules checking compliance in account C, those findings eventually need to be centralized for the security team, right? That's where delegated administration comes in.
Yes. Delegated administration is the essential connective tissue that makes the central security tooling account model work efficiently.
How does it function?
It's a feature within AWS organizations and specific integrated AWS services. It allows the org management account to designate a specific member account in the SRA context, typically the security tooling account, as the administrative owner for that service across the organization.
So you delegate guard duty management to the security tooling account.
Exactly. You delegate guard duty, you delegate Security Hub, AWS config aggregation, Macie, IAM Access Analyzer, Firewall Manager, and several others. Once delegated, the security tooling account can view findings, manage configurations, and sometimes take actions related to that service across all other member accounts within the organization.
So it ensures the security operations team maintains that single, consolidated, ideally real-time view of the security posture
Correct.
without needing to constantly switch roles or log into dozens or hundreds of individual application accounts to see what's happening. It's fundamental to centralized visibility and response.
Absolutely fundamental for operating security at scale within this model.
All right, we've built the structure, the house with its OUs and accounts, and we've put up the fences with SCPs. Now let's go inside that central security tooling account and really look at the sophisticated alarm system working. Let's start with the core of centralized detection and visibility.
Right, the eyes and ears. The absolute workhorse here, the first service most people enable, is Amazon Guard Duty.
Threat detection.
Yes, it's a managed threat detection service. It continuously monitors and analyzes several independent streams of data to identify potentially malicious or unauthorized activity. Specifically, it looks at AWS CloudTrail logs for API activity, VPC flow logs for network traffic analysis, and DNS logs for communication patterns.
And what's really crucial about how Guard Duty gets this data, you mentioned independent streams.
Yes, this is a key security feature. Guard Duty pulls these logs directly from the AWS control plane infrastructure. It does not rely on the customer having enabled logging to an S3 bucket first, nor does it depend on the S3 bucket policies being correct.
So it bypasses potential misconfigurations or even tampering at the S3 bucket level?
Precisely. If the log stream collection and storage is managed entirely by the customer, it's potentially vulnerable. An attacker who compromises a system might try to disable logging or delete the logs in S3 to cover their tracks.
Right.
Guard Duty's independent stream ensures the logs it analyzes are pristine and complete, directly from the source. It's a much more reliable input for threat detection.
Okay. That's a subtle but really important point. And where do Guard Duty's findings go?
All those high-fidelity threat findings, things like potential instance compromise, unusual S3 access patterns, CNC communication attempts, they flow automatically, usually within minutes, into AWS Security Hub CSPM.
Security Hub. So this is the central dashboard, the single pane of glass for security.
That's the primary goal, yes. But it actually does more than just aggregate alerts, as you hinted.
Okay.
Security Hub functions as a full cloud security posture management tool, CSPM. Yes, it aggregates and normalizes security alerts, which it calls findings from Guard Duty, but also from Amazon Macie, IAM Access Analyzer, AWS Config, Firewall Manager, and dozens of third-party partner tools.
So it brings everything together in one format.
One standardized format, yes. But beyond aggregation, it also runs continuous compliance checks. It often leverages service-linked AWS config rules under the hood to automatically assess your environment against security standards like CIS benchmarks, NIST frameworks, PCI DSS, and AWS foundational security best practices.
So it tells you not just about threats, but also about misconfigurations.
Exactly. It gives you both sides.
Yeah.
Active threats and potential weaknesses or compliance deviations. It really is intended to be the primary workspace for your security operations team, your incident responders, to triage alerts, prioritize findings based on severity, investigate issues, and manage the remediation efforts across the entire organization, all from one place.
Got it. Central hub for findings and compliance posture. Now, speaking of data security specifically, how does Amazon Macie fit into this central detection strategy? It focuses on S3, right?
Yes, Macie is laser-focused on data security within Amazon S3. It's an ML-powered data discovery and protection service.
How does it work?
It does two main things. First, it continuously evaluates your entire S3 bucket inventory across all accounts delegated to it. It looks at bucket policies, encryption status, public accessibility, replication configurations, providing a security posture assessment of the buckets themselves.
Okay, the container security.
Right. Second, and perhaps more powerfully, it runs sensitive data discovery jobs. You configure these jobs to actually sample and analyze the content of objects within your S3 buckets, using machine learning and pattern matching to identify sensitive data types.
Like PII, credit card numbers, credentials.
Exactly. personally identifiable information, PII, financial records, AWS secret keys, health information, PHI, custom data types you define. If Macy finds sensitive data that is, say, unencrypted or in a publicly accessible bucket or being replicated to an untrusted account,
Mm-hmm.
it generates a high-severity finding. And, just like guard duty, those findings are immediately fed into Security Hub for visibility and action by the security team. It helps answer the question, where is my sensitive data and is it exposed?
Okay. Crucial for data governance and compliance. Now, we've seen this massive shift in the industry, moving beyond just detection toward using formal logic and automated reasoning to actually verify policies before they cause problems. This is where AWS IMX Analyzer seems to fit in, particularly with its use of Zelkova technology.
Yes. This is, I think, one of the most exciting areas. IAM Access Analyzer represents a move towards what AWS calls provable security. It uses techniques based on mathematical logic and automated reasoning specifically, the underlying engine called Zelkova, to analyze policies and prove certain security properties about them.
Prove them mathematically.
Essentially, yes. It analyzes resource-based policies like S3 bucket policies, KMS key policies, Lambda function policies, SQSQ policies, and also identity-based policies attached to IAM roles. It looks for policy statements that grant access.
And what's the main type of finding it generates?
The most critical feature, especially in the SRA context, is its ability to generate external access findings. It proactively identifies any resource policy that grants access to an entity outside your defined zone of trust. Your zone of trust is typically your AWS organization or a specific list of trusted accounts.
So it flags if a bucket policy accidentally allows public access or access from some random third-party AWS account.
Precisely. And it does this based purely on analyzing the policy logic itself, using that automated reasoning. It doesn't wait for someone to actually try and access the resource. It tells you potential access paths exist that cross your trust boundary.
So it generates a warning based purely on the potential access defined in the policy text, not based on whether someone has actually logged in or used that access.
Exactly. It flags the potential for unauthorized external access before it can be exploited. It also generates findings for unused access, helping you identify roles or users with privileges they haven't actually used recently, further helping enforce that principle of least privilege.
Wow. That's proactive. Fixing policy errors before they become security incidents? Provable security.
That's a powerful concept. Proactive, provable security through automated reasoning. Now, to coordinate the enforcement of certain security policies consistently across all these accounts, especially for network security, the SRA relies heavily on AWS Firewall Manager.
Okay, Firewall Manager. What's its primary function in this big multi-account structure? It's not a firewall itself, right?
Yeah. No, it's an orchestrator, a management service. Its primary function is simplification and consistency of policy deployment for several other security services. Specifically, AWS WEF, AWS Shield Advanced, AWS Network Firewall Policies, security groups, and even Route 53 Resolver DNS firewall rules.
So you define policies centrally in Firewall Manager.
Yes. You, as the central security administrator operating from the Delegated Firewall Manager admin account, often the security tooling account, define security policies. For example, a baseline set of AWS WAF rules you want applied everywhere, or a standard network firewall policy for egress filtering. Crucially, Firewall Manager then automatically discovers resources across all your accounts, or specific OUs you target, that should have these policies applied, like ALBs, CloudFront distributions, VPCs. And it deploys and maintains those security policies across them.
Even for new resources.
Yes, that's a key benefit. It automatically applies the policies to new resources as they are provisioned, if they match the policy scope. It ensures that you maintain a consistent minimum security baseline across every application and environment without manual intervention for every new deployment. It's the central enforcement mechanism for these network and application security policies.
Okay, central policy definition and automated enforcement. That makes managing security across hundreds of accounts actually feasible. Let's pivot now to network defense, specifically the controls residing in that dedicated network account. The SRA strongly advocates placing perimeter services there. Why is pushing that defense right out to the network edge in that separate account considered so critical?
There are a couple of key reasons. Firstly, latency matters, especially for user-facing applications. And secondly, filtering malicious traffic as early as possible saves resources and reduces risk further down the stack. By placing services like CloudFront, your CDN, AWS WAF, Web Application Firewall, and AWS Shield Advanced, DDoS protection in the central network account and associating them with resources managed there.
Hmm.
You ensure that malicious filtering happens as close to the source of the traffic as possible. Often, this means filtering occurs right at the CloudFront edge locations scattered around the globe, potentially thousands of miles away from your core VPCs.
So you stop the bad traffic before it even gets close to your application servers.
Exactly. It never even attempts to enter your core network infrastructure in your region. This leverages AWS's massive global network infrastructure for defense and pushes the filtering capacity of services like Way right out to where the attack originates, improving performance for legitimate users and reducing load on your internal resources.
Okay, that makes sense. Let's talk about AWS Wave specifically. What kind of threats are we really talking about protecting against with Wave in this SRA model?
WAF is your primary defense against common web application vulnerabilities, the things you see in the OWASP Top 10. Think SQL injection, cross-site scripting, XSS, path traversal attacks, common protocol abuse. You configure rules, often using AWS-managed rule sets, to block these known patterns.
But it's more than just the basics now, right? WAF has evolved.
Oh, absolutely. Modern WAF policies are also increasingly tailored for more sophisticated threats. This includes advanced bot management, distinguishing good bots like search engine crawlers from bad bots trying to scrape content or brute force logins. It also includes capabilities like account creation fraud prevention using reputation lists and behavioral analysis.
And the SRA recommends layering these WAF rules.
Yes, a layered defense is often best. You might have a fairly general baseline set of way of rules associated globally with your CloudFront distribution in the network account, blocking known bad IPs, generic attack patterns. Then, you might have more application-specific, potentially more restrictive WAF rules associated with a regional resource closer to the application, like an application load balancer, ALB, sitting inside a VPC. Layering gives you both broad protection and specific tuning.
Okay. And for the really big volumetric attacks, the DDoS attacks, we have AWS Shield Advanced.
Right. Shield Standard is on by default for everyone, providing basic network layer DDoS protection. But Shield Advanced is the premium, managed DDoS protection service you subscribe to for enhanced safeguards.
What extras do you get?
Several key benefits. It provides more sophisticated detection and, crucially, automatic application layer, Layer 7, DDoS mitigation. It does this by integrating tightly with AWS. Shield Advanced can automatically create and deploy custom WAF rules in response to detected Layer 7 attacks, often without requiring manual intervention from your team.
So it reacts for you during an attack.
It can, yes. Additionally, if you subscribe to Shield Advanced, you gain 247 access to the dedicated AWS Shield Response Team, or SRT. These are DDoS experts at AWS who can assist you during an event, analyze traffic, and help fine-tune mitigations.
Okay, that sounds valuable, but the source documentation mentions a prerequisite for getting that proactive help, right?
Yes, this is critical. For the SRT to proactively monitor your protected resources and contact you during a suspected Layer 7 DDoS attack, you must enable the proactive engagement feature. And just as importantly, you need to have Route 53 health checks properly configured for the application endpoints you're protecting, like your ALBs or EC2 instances.
Why the health checks?
Because the SRT uses the status of those health checks as a key indicator of whether the application is genuinely impacted by an attack. Without health checks, they have less visibility into the application's actual health and might not engage proactively. So, configure Shield Advanced, enable proactive engagement, and set up robust health checks.
Got it. Essential steps for leveraging the SRT effectively. Now, connecting all these isolated accounts, the network account, the application accounts, maybe shared services, is also a significant network challenge in itself. The SRA recommends 3 main connectivity methods, each suited for different scale and complexity requirements. Let's run through those.
Okay, the simplest method, conceptually, but also the least scalable, is VPC peering.
Peering. Connect 2 VPCs directly.
Yes, it gives you full, private, bidirectional IP connectivity between 2 VPCs. Traffic stays on the AWS backbone. It's relatively easy to set up for a small number of connections.
But the limitations.
Scale and complexity. VPC peering is a one-to-one relationship. If you have, say, 10 VPCs that all need to talk to each other, you end up with a complex mesh of 45 peering connections to manage. It just doesn't scale gracefully beyond a handful of VPCs.
Yeah.
Also, peered VPCs cannot have overlapping IP address ranges, CIDR blocks.
Okay, good for simple cases, bad for large meshes or overlapping IPs. What's the next option? AWS Private Link.
Correct. Private Link offers a very different model. It provides private unidirectional client-server connectivity between VPCs.
Unidirectional.
Yes. You expose a specific service, like a database, an internal API, or even a partner service, running in one VPC the service provider VPC, as an endpoint service. Consumers in other VPCs, the client VPCs, can then create an interface endpoint in their VPC to connect to that specific service endpoint. Traffic flows only from the client to the service provider endpoint over the AWS network.
Ah, so it's not full VPC to VPC routing, just specific service access.
Exactly. It's fantastic for securely exposing just a particular service endpoint without allowing general network access between the VPCs. And a major advantage. Private Link does support scenarios where the client and server VPCs have overlapping IP addresses, which is very common in large organizations, especially after mergers or when connecting to third-party SaaS providers using Private Link.
Okay, private, one-way, service-specific access handles overlapping IPs. Good for specific use cases. But for the true enterprise scale, connecting dozens or hundreds of VPCs, the backbone of the SRA's network connectivity is usually AWS Transit Gateway.
Absolutely. Transit Gateway provides the highly scalable, fully managed hub-and-spoke network topology design.
How does that work?
You deploy a Transit Gateway, typically in your central network account. That's the hub. Then all your other VPCs, application VPCs, shared services VPCs, etc., and even your on-premises networks via VPN or Direct Connect attached to this central transit gateway. They become the spokes.
So everything routes through the central hub.
Yes. The transit gateway acts as a cloud router. You manage routing centrally within the transit gateway's route tables. This connects hundreds, even thousands of VPCs and on-premises networks together far more efficiently than managing countless individual peering connections or complex VPN meshes. It drastically simplifies the overall routing and network topology management in a large, multi-account organization. It's built for scale.
Okay, Transit Gateway for the complex, large-scale hub-and-spoke connectivity. That makes sense. Now let's finally move into the application account itself and discuss security applied directly to the workload, where the code runs and the data lives. Let's start with compute hardening, specifically for EC2 instances.
Right. A crucial baseline security step for EC2 instances, mandated by security best practices and often compliance frameworks now, is the required use of Instance Metadata Service version 2, IMDS v2.
IMDS v2. I know v1 had some issues. This is the newer, more secure version.
Yes, it's a significant security improvement over the original IMDS v1. The key difference is that IMDS v2 enforces session-based authentication. Accessing the instance metadata endpoint requires obtaining a short-lived session token first, and then using that token in subsequent requests.
And why is this session token requirement so important? What specific threats does IMDS v2 mitigate that v1 didn't handle as well?
The primary threats that IMDS v2 is designed to mitigate are those that exploit the ability of code running on an instance, or sometimes code running elsewhere that can trick the instance, to freely access the instance metadata service, which often contains temporary IAM credentials.
Ah, credential theft from metadata.
Exactly. The big one is server-side request forgery, SSRF. This is where an attacker finds a vulnerability in your web application that allows them to trick the application server into making arbitrary HTTP requests on their behalf. With IMDS v1, they could potentially make a request directly to the metadata endpoint, usually 169.254.169.254, and steal the temporary IAM credentials associated with the instance's role.
Which could give them AWS API access.
Potentially significant access, yes. IMDS v2's session token requirement makes this SSRF attack much, much harder because the attacker first needs to be able to make a PUT request to get the token, which is often blocked, and then use that token. It just adds a significant hurdle.
Does it help with other things too?
Yes. It also mitigates risks from things like open reverse proxies configured on the instance, or vulnerable third-party software like certain firewalls or monitoring agents running locally that might inadvertently expose the metadata endpoint. IMDS v2 effectively prevents those temporary credentials from being easily siphoned off a host, even if there's a vulnerability present. Enforcing IMDS v2 is a non-negotiable baseline for SRA compliance.
Okay, mandate IMDS v2 everywhere. Got it. Next up, managing identity for applications, specifically focusing on removing secrets like passwords and API keys directly from the application code.
Yes, this is another critical principle. We rely heavily on AWS Secrets Manager for this.
Secrets Manager, its job is pretty clear from the name.
Right. Its core function is to protect sensitive secrets, things like database credentials, third-party API keys, external service tokens, by replacing hard-coded secrets within your application code or configuration files with a programmatic API call to retrieve the secret at runtime.
So the secret isn't stored with the app.
Exactly. The application fetches it securely when needed. Secrets Manager also handles the secure storage of the secret itself, encrypting it at rest using AWS KMS. And, importantly, It can manage the automatic rotation of secrets, like database passwords, according to a schedule you define.
Rotation is key, minimizes the window of exposure.
Absolutely. Regularly rotating secrets ensures that even if one is somehow compromised, its useful lifetime is very short. Secrets Manager helps automate that often painful rotation process, improving security posture and consistency between, say, development and production environments.
Where should Secrets Manager typically be configured or managed? In the app account or centrally?
That's a good question, and the SRA guidance suggests a pragmatic approach. The general best practice for placement is to configure and manage Secrets Manager close to where the secrets are actually used. So typically within the application account itself. This aligns with the principle of least privilege. The application's role only needs access to secrets within its own account boundary.
But sometimes centralization might be needed.
Yes, in some cases, strict governance requirements or the need for a central team to manage secrets across many applications might dictate centralizing secret creation and management in the security tooling account, and then using resource-based policies to grant cross-account access to the applications that need them. But the default recommendation is usually in-account management for simplicity and tighter scoping.
Okay, manage secrets close to the consumer unless governance dictates otherwise. Finally, let's touch on something really at the cutting edge of authorization, moving beyond just IAM roles. Amazon Verified Permissions and the associated policy language, CEDAR.
Right, this is pushing towards that provable security idea again, but this time applied to fine-grained application authorization decisions. Verified Permissions is a scalable, standalone authorization service.
What does it let you do?
It lets you externalize and centralize your application's authorization logic. Instead of embedding complex if-then-else permission checks directly within your application code for who can access what data or perform what action, your application makes a call to verified permissions, passing details about the user, the action they're trying to take, and the resource they want to act upon. Verified permissions then evaluates this request against policies you've defined and simply returns an allow or deny decision back to your application.
So the authorization logic lives outside the app code.
Exactly. And the engine for defining and evaluating these policies within verified permissions is CEDAR. CEDAR is an open-source, security-first policy language. It was designed from the ground up with safety and analysis in mind, and it's built using some of those same automated reasoning principles we talked about with Zelkova for IAM Access Analyzer.
So instead of writing potentially complex, maybe error-prone IAM identity or resource policies for every single application action, you define more generalized, perhaps more readable policies in CEDAR.
That's the goal. CEDAR allows for highly granular contextual authorization logic. You can write policies like, allow a user in the managers group to view a document resource only if the resource is tagged with Project Alpha and the request occurs during business hours and the user has authenticated with MFA.
Wow, that's very specific. Much more context than typical IAM.
Much more context. It really facilitates enforcing principles like default deny and least privilege at a very fine-grained level, potentially at a scale and complexity that traditional IAM resource policies might struggle to achieve cleanly within an application context. It helps implement a zero-trust approach by making authorization decisions explicit, external, and auditable. It's still evolving, but it's a very powerful direction for application security.
Okay, we've spent a lot of time on proactive defense, building the walls, setting up the alarms, but we have to shift now to reactive readiness. What happens when something does go wrong? The SRA provides pretty detailed guidance here too, often built around the familiar NIST framework for incident response, which outlines, I think, 6 phases.
That's right. The SRA guidance aligns well with the standard incident response lifecycle phases. Those are generally preparation, then detection and analysis, followed by containment, eradication, recovery, and finally, post-incident activity, like lessons learned.
6 phases: preparation, detect, analyze, contain, eradicate, recover, post-incident.
Exactly. But it's really important to stress, and the SRA documentation explicitly calls this out. These phases are guidance, and they do not necessarily happen sequentially in a neat, linear fashion.
Ah, okay. It's not always step 1, then step 2.
Not at all. In a real incident, you often find yourself looping back. For example, analysis might continue during the containment and eradication phases as you uncover more information about the attacker's TTPs or the scope of the compromise. You might contain one system, then analysis reveals another is compromised, so you loop back to containment. It's iterative.
Okay, flexible guidance, not rigid steps. Let's focus first on preparation. Given the complexity of a multi-account AWS environment and the sheer speed at which things operate in the cloud, the SRA mandate here seems crystal clear. Automation is mandatory for effective forensic capabilities.
This is probably one of the most critical investments you can make before an incident. Manual collection of forensic evidence, memory dumps, disk snapshots, logs across potentially hundreds of instances spread across multiple accounts and regions is just. It's not feasible during a real incident.
Why not? Too slow, too error-prone.
Both. It's incredibly time-consuming, which gives the attacker more dwell time to pivot deeper into your environment or cover their tracks more effectively. And perhaps even more importantly, manual collection is highly prone to human error. Someone might forget a step, click the wrong button, modify evidence inadvertently.
Which could invalidate it for legal purposes or internal investigation.
Exactly. It compromises the integrity of the forensic process. So, robust preparation requires building, testing, and maintaining automated workflows for evidence acquisition and preservation.
What else does preparation involve, according to SRA?
It involves clearly defining roles and responsibilities for incident response. Using a RACI chart, responsible, accountable, consulted, informed, is highly recommended to avoid confusion during a crisis. It means training your staff specifically in cloud incident response techniques and the automated tooling you've built. And critically, it means running regular simulations.
Like fire drills, but for cyber attacks.
That's precisely. Mock cyber events, tabletop exercises, maybe even controlled red team engagements. These simulations must mimic current threat actor tactics, techniques, and procedures, TTPs, as closely as possible. The goal is to validate your automated response playbooks, test your team's decision-making under pressure, and build that crucial muscle memory for when a real event occurs. Preparation is everything.
Okay. And how does the SRA suggest we measure the effectiveness of this preparation and our response capability? They define some key success metrics using 3 mean times: MTTA, MTTR, MTTC.
Yes, these metrics are crucial for understanding and improving your IR process. First, you have mean time to acknowledge, MTTA.
MTTA. What's that measure?
This is the time lapse from the moment a security alert actually fires, say, a guard duty finding appears in Security Hub, to the moment a human analyst on the security team actually recognizes it, validates that it's likely a real issue, not a false positive, and officially prioritizes it for investigation. Reducing MTTA is about improving your monitoring, alerting fidelity, and triage process.
Okay, time to notice and prioritize. Next is mean time to respond, MTTR.
Right. MTTR measures the time from that initial alert firing until the security team takes the first responsive actions. This might be initiating an automated forensic snapshot workflow, isolating a potentially compromised host from the network, blocking a malicious IP address at the WAF, or starting deeper log analysis. It's about how quickly you can start acting on the alert.
Got it. And the third one, which seems like it directly determines the actual impact, the financial and reputational cost of the incident, is mean time to contain, MTTC.
MTTC is arguably the most vital metric from a business impact perspective. It measures the total time elapsed from the initial alert until responsive actions are successfully completed that effectively prevent any further harm or spread by the attacker. This is when you've stopped the bleeding.
So shorter MTTC means less damage done.
Exactly. A shorter MTTC is probably the single best indicator of a mature, effective security incident response program. It directly minimizes the scope of the incident, the impact on systems and data, and the overall exposure time for the organization.
Yeah.
Driving down MTPC should be a constant goal.
Okay, focus on reducing MTTA, MTTR, and especially MTTC through preparation and automation. Now, for the forensic strategy itself when an incident occurs, the SRA makes a strong recommendation, mandating the creation of a dedicated forensics account, separate even from the central security tooling account we discussed earlier. Why the need for yet another dedicated security environment? Seems complex.
It does add complexity, but the separation is necessary for several key reasons, primarily revolving around differing access requirements, data handling needs, and maintaining the integrity of the forensic process itself.
Okay, different access needs.
Yes, forensics personnel during an investigation often need highly elevated, temporary, and very specific permissions to access resources within potentially compromised application accounts, things like taking memory dumps, disk snapshots, accessing logs directly. These permissions are often broader or different from the standard permissions granted to the general security administrators working day-to-day in the security tooling account. Separating the accounts helps enforce least privilege for both roles.
Makes sense. What about data handling?
The forensics account needs to handle 2 fundamentally distinct types of potential evidence. First, there's AWS control plane data, like CloudTrail logs showing API calls the attacker made. Second, there's customer data plane artifacts, which could include sensitive customer data residing within OS memory images, disk snapshots, or application logs.
Ah, so it might contain PII or other regulated data from the compromised system.
Potentially, yes. Isolating the forensics account allows you to apply much stricter access controls, potentially subject to legal holds or chain of custody requirements, specifically around this sensitive evidence. It also provides a secured, non-production lab environment where forensic analysts can perform malware analysis or reverse engineering on suspicious artifacts without running afoul of AWS terms of service regarding malicious activity, and without risking contamination of your production or even security tooling environments.
Okay, separation for access control, legal holds, and safe analysis. And the SRA has a specific rule regarding the deployment of this forensics capability across AWS regions, doesn't it?
Yes, this is an important operational detail. The SRA guidance strongly recommends, essentially mandates, that the core forensics account capabilities, including the automated evidence collection functions, secure storage buckets, often called evidence lockers, and potentially analysis tooling must be deployed and available in every available AWS region where the organization operates, even if you're not actively running workloads in all of them today.
Every region. Why?
Data residency and sovereignty. This mandate ensures that if an incident occurs involving resources in a specific region, say Frankfurt, you can conduct the entire forensic investigation, collecting the evidence, storing it, analyzing it within that same geographic region. This helps you adhere to data residency requirements, like GDPR or other local regulations, that might restrict moving potentially sensitive forensic artifacts across borders. Deploying forensics capabilities regionally avoids that compliance headache during a high-stress incident.
Okay, regional forensic capabilities for data residency compliance. That's smart planning. Now let's get really practical. The SRA details a precise sequence of steps for responding to a suspected compromised EC2 instance. This seems like an absolutely critical playbook designed to preserve volatile evidence before it disappears. There's an 8-step sequence.
Yes, and the order is crucial because it prioritizes capturing the most volatile data first, the stuff that disappears if you reboot or even sometimes just interact with the system, while also taking steps to contain the damage and preserve the persistent evidence. You have to move quickly, but methodically in the right order.
Okay, walk us through it. Step 1.
Step 1. Acquire instance metadata. Before you touch the instance itself, grab all the identifying information, the instance ID, the private and public IP addresses it had at the time, the VPC ID, Hubnet ID, attached security groups, IAM role, launch time. This is ephemeral configuration data that defines the system's identity and context, and it might change or be lost. Document it immediately.
Okay, capture the context. Step 2.
Step 2. Enable instance protections and apply tags. Immediately turn on EC2 termination protection for the instance to prevent accidental deletion. Also, critically, change the instance's shutdown behavior setting to stop if it happens to be set to terminate. You don't want it disappearing if someone stops it. And apply automated quarantine or forensic investigation tags. These tags should ideally trigger automated security group changes or network ACL rules to start isolating the instance.
Proactive tagging for automation. Step 3.
Step 3. Acquire volume snapshots. Take snapshots of all attached EBS volumes. This preserves the persistent disk evidence, the file systems, logs stored on disk, installed applications. Snapshots are point in time and relatively quick to initiate.
Disk image secured. Step 4 sounds critical.
Step 4. Acquire memory image. This is often the most critical evidence acquisition step and also the most time-sensitive and potentially complex. Capturing the volatile RAM contents is crucial because memory contains running processes, active network connections, loaded kernel modules, potentially encryption keys, passwords typed interactively, command history, tons of valuable forensic artifacts that are not stored on disk and will be lost if the instance is stopped or rebooted.
So memory first after basic protections, then disk. Got it. Now, step 5 is listed as optional and comes with a big warning. Perform live response or artifact collection.
That's right. This step involves running commands directly on the live, potentially compromised instance to collect specific files, process listings, network connection details, etc. It's generally discouraged in the SRA guidance unless disk or memory acquisition fails or you have a very specific targeted need.
Why discouraged? Seems useful.
Because any interaction with the live system, any command you run, modifies the system state. It changes file access times, potentially overwrites data in memory or on disk, like in shell history files, and alters the very evidence you were trying to preserve in a pristine state. If you absolutely must perform live response, you need extremely well-defined, minimal procedures, and you must meticulously document every single command executed and its output, acknowledging that you have altered the evidence. Memory and disk snapshots are forensically cleaner.
Okay, live response is a last resort due to evidence modification, step 6.
Step 6. Decommission the instance from service. If this instance was part of an application stack, you need to take it out of active duty, detach it from any auto-scaling groups it belonged to, deregister it from any elastic load balancers, ALBs, NLBs that were sending traffic to it, stop it from serving production traffic or interacting with other production systems.
Take it offline functionally, step 7.
Step 7. Isolate or fully contain the instance network-wise. This is where you ensure it can no longer communicate. Modify its security groups to deny all inbound and outbound traffic, except perhaps allowing access from your trusted forensic analysis environment. You might also apply network ACLs for broader subnet-level isolation. The goal is to completely end and prevent all current and future network connections to and from the compromised instance. This is the moment you truly stop the bleeding from a network perspective.
Cut it off completely. And finally, step 8 seems like the logical conclusion.
Step 8 is often described as the responder's choice, post-acquisition. Shut down the system. Once you have successfully acquired the critical volume snapshots and, most importantly, the volatile memory image, it is generally recommended to stop the EC2 instance.
Why stop it then?
Stopping the instance prevents any further malicious activity originating from it, stops it from consuming resources, and ensures it remains in a stable state, consistent with the snapshots and memory image you captured. You only do this after you've secured the volatile evidence. Don't stop it before getting the memory dump.
Right. Preserve volatile data, then stop. Okay, that 8-step process is a critical playbook. Once containment and evidence acquisition are done, we move to eradication and recovery.
Correct. Eradication focuses on identifying and removing the root cause of the incident and any artifacts left behind by the attacker. This means finding the initial vulnerability, removing any malware or backdoors, identifying and deleting any unauthorized IAM users or roles the attacker created, cleaning up unauthorized access policies, terminating any rogue resources they might have launched.
And what's the key activity here, especially regarding data and credentials that might have been compromised?
A key eradication and recovery activity, based on the principle of assuming compromise, is to re-encrypt all sensitive data, and also any EBS volume snapshots taken before or during the incident using a brand new AWS KMS Customer Managed Key, CMK.
A new KMS key. Why?
Because if the original KMS key itself or the IAM credentials allowing access to it were potentially compromised during the incident, then simply restoring data encrypted with that old key doesn't fully mitigate the risk. The attacker might still have access to the key. Re-encrypting critical data and snapshots with a fresh, uncompromised KMS key ensures that even if the old key was leaked, the restored data remains secure going forward. It's a vital step for ensuring a clean recovery.
Assume key compromise. Re-encrypt with a new key. That's thorough. Eradication also involves patching the vulnerability, cleaning up everything the attacker did before finally moving to recovery and restoring systems to a known, safe operational state.
Exactly. And then, of course, the post-incident phase, learning lessons and improving defenses. But that sequence contain, acquire evidence, memory first, isolate, eradicate, including rekeying, recover. That's the core response flow. Hashtag outro.
Wow. Okay, we have covered a tremendous amount of detail on the AWS security reference architecture today. It's really quite comprehensive. We established the absolute necessity of that multi-account structure for isolation, for limiting that blast radius.
We mapped out the precise roles of those specialized accounts, like the security tooling account being the central nervous system, the log archive being the immutable vault.
And the application of those powerful centralized preventive guardrails, like service control policies, using either deny lists or the more restrictive allow lists.
We also detailed the defense in depth approach within the architecture, using those automated detection services like GuardDuty, Macie, IAM Access Analyzer operating centrally.
Right, feeding into Security Hub.
And coordinating network perimeter controls like WF and Shield Advanced, typically managed from the network account.
And crucially, we mapped out the requirements for true forensic readiness in the cloud, emphasizing that automation is key, the need for a dedicated forensics account deployed regionally, and following that strict, ordered sequence of steps required to preserve volatile evidence from a compromised cloud resource like an EC2 instance.
Yeah, the SRA really provides a solid blueprint covering structure, prevention, detection, and response.
You know what really stands out to me, reflecting on all this, is the deep philosophical shift it represents in how security is being built and validated in the cloud. It feels like it's moving away from just traditional configuration management and checklists
Hmm.
towards something more rigorous, almost like provable security, where the architecture's soundness needs to be logically verifiable from the outset.
I think that's a fantastic observation. Absolutely. We saw clear examples of that trend woven throughout the SRA principles and tooling.
Where specifically?
Well, most obviously with AWS IAM Access Analyzer, its use of the Zelkova automated reasoning engine to mathematically analyze policies and prove whether they allow unintended external access. That's the epitome of provable security applied to permissions.
Right, finding flaws in the logic before they're exploited.
And again, with Amazon verified permissions and the Cedar policy language, designing a language specifically for authorization that is inherently safer, more analyzable, and allows you to externalize and enforce fine-grained contextual authorization based on logical rules that's moving in the same direction. The tools themselves are essentially helping you write and validate security policies as code that is then enforced centrally and automatically.
So the era of just relying on periodic manual audits, gut feelings, and maybe overly long lists of permissive firewall or IAM rules, that seems to be rapidly drawing to a close, at least the sophisticated environments following this kind of model.
I think that's absolutely the key takeaway. And maybe that leads us to the final provocative thought for you, the listener, to chew on after this deep dive.
Okay, leave us with something to think about.
The AWS SRA, in its structure and its reliance on these advanced tools, clearly demonstrates that in the modern hyperscale cloud, security is increasingly becoming a discipline built not just on human expertise and oversight, but profoundly on automated reasoning, policy as code, and verifiable logic. The real deep dive for the future, the next level of mastery, might not just be learning the intricacies of each individual cloud service, but learning how to effectively design, manage, and critically learning how to trust the automated logic in the machines, the guard duty algorithms, the Zelkova provers, the Cedar engines that are increasingly designed to protect your cloud environment at a scale and speed that no purely human team could ever hope to achieve alone.
Yeah.
Can we learn to trust the machines that secure the machines? That might be the next frontier.